who are here, and thank you, Rasoul, for giving this talk. So, just as an introduction, so Rasoul is really a sort of an interdisciplinary or multidisciplinary scholar working at the intersection of computer science and economics, with interest in sort of various areas. From multi-agent systems to mechanism design, and formalizing cryptographic protocols and so on. So so my contact with Rasoul was because of sort of my interest in learning more about sort of mechanism design approaches to designing blockchain protocols. And Rasoul has done some really interesting work. He's a recent winner of the ACM Global Challenge in Economics and Computation with two economists. And in addition to his research, he's also product designer and product owner of the Parse decentralized finance ecosystem. And there's a lot more information that he has on his website. So he had offered to talk about mechanism design approaches to blockchain consensus protocols, and I thought this was a great opportunity for me and others to learn from him. So thank you, Rasoul, for giving this talk, and welcome.
Thank you, Arish. Thank you so much for your introduction, and thank you so much for this opportunity and having me. So please let me share. Do you have my screen?
Yeah.
Yeah, thank you. Thank you, everybody, and good morning and good night. So the title of my talk is Game-Theoretic. Blockchain is a game-theoretic cryptographic ledger. And I'm going to, first of all, talk about multi-agent systems and and talk about two specific topics in multi-agent system: cryptographic protocols and mechanism design, economic mechanism design. Then I'm going to talk about centralized and decentralized ledger and what's the difference between these two ledgers. And then I am going to propose a set of axioms, actually incentivize axioms for decentralization. And finally, I'm going to talk about game-theoretic security. Multi-agent systems. Let's start and see what a multi-agent system is. Actually, a multi-agent system is a set of agents, consists of a set of agents. But these agents, it's not just a set. These agents have interaction with each other. And different interactions are studied with different theories. For example, when we think of secure communication between them, then the multi-agent system is security protocol design, and security protocols are studied for this purpose. When we think in a multi-agent system that rational agents actually compete with each other, then we are going to talk about game theory and find the equilibrium of the system. And when we think of incentives, and we think that actually agents are going to obey some rules and do some instructions, then the study is going to economic mechanism design. We also have social networks as another type of multi-agent system. When agents interact and actually connect with each other, and how they form different networks with each other, economic networks based on their utility, they can connect to different peoples. So, for example, in labor markets, we have different networks between agents. So social networks, small world properties, and different properties are studied in the topic of social network. Another topic for multi-agent system is form coalitions. People does not just compete with each other. Sometimes they need to form coalitions to get more benefit and to maximize their utility. So here, cooperative game theory is the solution and is the topic that is going to study form coalitions. So this is why multi-agent system, when we say multi-agent system, when we say someone is working on multi-agent system, it means that he can work in several different interdisciplinary and multidisciplinary topics. Actually, in a multi-agent systems, the utility of the agent is not just depend on his own action, and it depends on the state of the system. And the state of the system is produced and is constructed by the action of all agents. So if I want to maximize my utility, I need to pay attention to the actions of others, and my utility function is a function from the profile, the strategy profile of all agents, not just one agent. Now, what's the relation between blockchain and multi-agent system? Actually, blockchains are multi-agent systems. Where nodes, sometimes we call them nodes or agents in this talk, peer-to-peer securely communicate. So security protocols and cryptographic protocols are important here. Compete to produce the next block, and for example, in proof of work consensus mechanism, or in proof of stake, they need to have incentives to contribute their stake or computational power. So here, the mechanism that we are going to develop and construct, mechanism should be incentive compatible. Otherwise, the rules that we considered for the blockchain does not work at all. The other thing is that a blockchain, when a user wants to ask to send a request and says, okay, please write my data on this blockchain, all the nodes, all the agents who run the blockchain should have incentive to propagate the data in the network, to connect to other agents. So having incentive to propagate also and considering as a network is really important. Also, the form coalition happens also in blockchain. We have lots of mining pool, staking pool in different consensus mechanisms based on Ethereum, Bitcoin, that people form pools to have a more power to mine the other block and have more rewards, or they decrease their risk by joining the pool in sometimes. So forming pools also studied in blockchain. In this way, blockchains are multi-agent systems and their topics are multi-agent systems. Cryptographic protocols, as I said, one of the topics of multi-agent system is cryptographic protocols.
Rasoul, if I can ask a question on the previous two slides, I think that was a very helpful sort of framework. Now, within sort of blockchain, written sort of academic research on sort of the role of multi-agent systems in blockchain implementations, have all of these different sort of aspects been covered, or are some covered more than others? So, certainly I think, the security aspect is something that's probably been covered quite a bit. How much research has been done into sort of mechanism design, how much into, some of the other aspects. So can you give us a quick sort of a summary of that?
Yeah. If blockchain is studied as a distributed system. When we say distributed systems, they are much attention to the network. It is studied as a game theory, and for example, they are going to prove that in following the longest chain is an equilibrium or not, and it is much studied using game theory, but there are still very open questions there, and that we can think of them. Some few works are done in mechanism design, actually, in after 2020, just 4 or 5 papers, and two different actually ways is between the relation of blockchain and mechanism design. Some of them study blockchain as a mechanism design. Some others say, okay, we are going to design a mechanism how we can use blockchain to consider privacy for our users. Not the aim is not blockchain. The aim is mechanism design. And we won't just use this technology to design new auctions, to design new matching solutions, but these matching solutions, these auctions, these mechanisms could have considered privacy of the agents and be traceable. So in mechanism design, there are two ways of the study. I think in those topics that are going to base on cryptographic and security, we do not have much interesting problem. But in game theory, we have lots of interesting problems. Since blockchain technology is much forward than academia, and academia is yet need to work to reach to the technology. There are lots of different proof of stake consensus mechanisms, not just one proof of stake mechanism. So, and they did not study that what is, for example, the equilibrium of this mechanism, or these mechanisms are incentive compatible or not. So yeah, as the industry is going faster in blockchain, I believe that we have lots of to do as academia in this area.
Yeah. So again, I don't want to sort of take too much time, but I just wanted to mention one sort of comment or question. So within mechanism design, there's also, or related to mechanism design, there's also this growing literature on information design coming out of economics. And to me, it seems like blockchain systems are really about information design as well, right? What information you choose to reveal by putting it on a blockchain or something like that. So, some organizations have to think about, like in a supply chain, as a supplier, I might want to reveal kind of the source of my inputs or whatever. And so information design is also, it seems to me, an interesting part of this, but I haven't seen too much research on information design approaches to blockchain systems. So I was just curious if you had a comment about that.
Actually, it's interesting, but I really do not have any specific comments. I believe that in information design, two things are important. For example, if I want to reveal an information, what is my incentives at first? And then how are you are going to consider my privacy? And for example, suppose that we are going to make a data market so that people can sell their data. We know that from data we can drive lots of other things. Data analysis process can be done on data, on the raw data, and drive some things that the owner of data do not like to reveal it. So we should find out if I'm going to reveal an information, what I'm going to reveal. Maybe I want to avoid to reveal some knowledge, and here consider some privacy on this information. To whom? So we should think of access control also. Maybe some mechanism on access control. Who has access to this information, who can reveal this part, and what that information says. But actually, I did not study those parts in information design. I would be happy to know more about it. Thank you.
Thank you.
So let's talk about cryptographic protocols. Actually, blockchain is cryptographic protocols plus incentive mechanism design. If I want to say what is a cryptographic protocol is a finite sequence of cryptographic message, sequencing some cryptographic message to reach to a purpose. This message is between some agents. For example, Needham Schroeder public key protocol says that agent A sends a message. This message contains the name of the sender and also a nonce generated by the sender and encrypted with the public key of the receiver B. And then B responds A by sending a nonce that he's going to generate himself and concatenate with the nonce of the A, and they are encrypted with the public key of A. And then A receives the message. A is going to respond B and send him a nonce that is generated by B and encrypted by public key of B. So through this sequence, A and B handshake with each other, and that they are going after that start another protocol. So that's the protocol, and actually this protocol has some attacks on this protocol. Cryptographic protocols are designed to fulfill actually various security aims. For example, distributed a shared key, a symmetric key, this non-repudiation, anonymity, authentication, and the most important thing is that how we are going to sequence this message and how we are going to construct this cryptographic message, what we are going to put in this message. Maybe without a timestamp, we would have a replay attack. Without the name of the sender, we would have the man-in-the-middle attack. So what are we going to put in the messages, and design the messages is really important in security design. And if we consider and design the messages that are sent between agents appropriately, then we could reach to for security purposes. The other topic of multi-agent systems that I'm going to talk is incentive mechanism design. As I said, blockchain is the combination of cryptographic protocols and incentive mechanism design. What is mechanism design? Mechanism design is the reverse of game theory. In game theory, we say, okay, we have a multi-agent system. Each agent has his own utility function and wants to maximize his utility. And we find what is the equilibrium. What is, for example, Nash equilibrium. But in mechanism design, we're going to design the game. We say, okay, we want to reach to this state. We want that rational agents in this multi-ledger system stay in this stage and reach to this state. So we're going to design rules and instructions, and these rules and instructions should be incentive compatible. Two things in here is important. Who runs the instructions? Agents. So incentive of agents is the fuel of the mechanism design. And if the mechanism does not incentivize them, then the rules and the instructions are not going to actually apply. So nobody's going to apply those instructions. So it is really important that the mechanism should incentivize them to do instructions. The other things that the rules of the mechanism should be incentive compatible, and nobody has incentive to deviate the rules. In designing a mechanism, actually, in mechanism design, we have three main concepts: incentive compatibility, efficiency, and fairness. Pareto efficiency. We have several different notions of efficiency and several notions of fairness. And also we have several different impossibility theorems that says these three concepts are not possible in different situations. So as I said, the incentive of agents are the fuel of the mechanism and cause the mechanism to work, and some specific applications and topics are social choice functions, voting mechanisms, first price and second price auctions, order book, kidney matching algorithm, Gale-Shapley algorithm, and other topics, hold-up problem, bankruptcy problem, social choice, course allocation. A new topic, actually, that we hear is a smart contract. A smart contract that says, okay, we already know what is a contract between people, but a contract could be a code, could be an immutable code, and actually the multi-agent system, the agent in a multi-agent system, interact with each other through this code. So this code is the rule. This code is the contract, and we may think of proof of work and proof of stake also as a computer code contract. For example, in proof of work, miners knows that how to compete with each other, and who is going to determine the rules of this game? A code, okay, the code of the consensus mechanism. In proof of stake, also miner validators know what to do, and who is going to determine the rules is a code. So here, a smart contract are new kinds of applications of mechanism design. Actually, we can say these are actually a new kind of mechanism design. Designing a smart contract is designing a mechanism. If our code is not designed truly, then nobody is going to have incentive to follow it. Nobody have incentive to interact with our smart contract. Smart contracts have several applications actually in different topics. For example, in centralized finance, in decentralized exchange, automated market makers, we have Uniswap and Bancor are two platforms. In decentralized lending borrowing platform, also Aave is important. DAOs, stable coins, autonomous supply chains, tracking shipments. So these are all smart contracts. We can design a smart contract for a smart factory, for a smart city, and ask citizen of a city interact with each other through that smart contract. So it's a new kind of mechanism design, I believe.
Rasoul, so again, I find this interesting and helpful. So, but let me ask maybe a couple of clarifying questions. So, you talk about sort of the protocols like proof of work and proof of stake, and you talk about smart contracts as being both sort of illustrations or examples of mechanism design. So my first question is, so in some sense, we can think about some of this as sort of ex-ante mechanism design and some as ex-post. And what I mean by ex-ante and ex-post in this context is like you need to design the proof of work mechanism or the protocol or whatever we want to call it, just so that agents have an incentive to use the system, participate, and so on and so forth. In that sense, it's ex-ante. And smart contracts. Again, I think a lot in context of supply chains, but smart contracts I see as ex post, right? So what I mean by ex post is traditionally there may be a lot of inefficiencies where ex post there's a lot of haggling, like people argue with each other. So one of the good examples of smart contracts that in the supply chain context I've seen is, Walmart in Canada used to get into a lot of billing disputes with the trucking companies that would deliver stuff to their warehouses. And the billing disputes were around, was the shipment arriving on time, et cetera, et cetera, et cetera. But through smart contracts, they were able to eliminate all of these because it's on the blockchain, what time, there's a timestamp when the truck arrived. Exactly. So there's no need to argue, right? So these kind of exposed things are fixed due to smart contract. And ex ante, you also, whether it's proof of work or proof of stake, these things work. So I mean, in that setting, I find this kind of your framework of mechanism design for consensus protocols and mechanism designs for smart contracts helpful. So I just wanted to ask you, does this sort of match with my way of thinking about it in terms of sort of ex ante incentives and ex post incentives?
Yeah. I think it's a great categorizing. For example, the decentralized lending borrowing, I know that how is going to the interest rate is computed, and it is done by code. So it's still interesting. Nobody's going to compute the interest rate in a lending borrowing platform, and it's not a game actually. I have an incentive that I was doing it in the real world as well. Yeah, in the real world also there are lots of banks who do the services of lending borrowing, but we are going to put it in the blockchain and do it using a smart contract, and it would be more transparent. Yeah, we have here transparency, and the code decides to do to punish someone who, for example, is not going to pay monthly, and there is no nothing that is, we do not know, for example, when I'm going to lend my money, I'm sure that is going to borrow to every possible person, not to just specific persons there. So yeah, here are all the contracts that we use in our real world, but in proof of work and in proof of stake, actually, in those consensus mechanisms, they are going to make a game. They are going to, there is a code that provides us a game to make something valuable. Yeah, these are different, actually.
Yeah.
Yeah. Okay, let's talk about centralized and decentralized ledger. I'm going to say, actually, simply, what is a blockchain? A blockchain is a notebook, is a ledger, where each page of the notebook is called block, and its punch is done by cryptographic primitives. So simply, what is a blockchain? A blockchain is a notebook, each page is a block, and when we want to punch this page to the previous page, it is done by cryptographic primitives. And cryptography, just here, it is seen in making a blockchain. But actually, blockchains that we know is Bitcoin and Ethereum and all the blockchains that we know, they are decentralized ledger, not centralized ledger. And they have consensus mechanism to make the in these agents to have consensus and agreements on this ledger, on this notebook. In proof of work, punching actually is done by hash puzzles, solving hash puzzles, and in proof of stake, punching is done by a digital signature of validators. Let me first of all explain a simple centralized ledger. In a centralized ledger, we have an agent, say Alice. Alice is the owner of the ledger, of the notebook, and users who have requests to write their data, their transactions, or any other data on the ledger, they send their data to the Alice. Alice receives the data and then check the consistency of the data with the previous pages. After that, he's going to create a new page and write the data on the new page and punch the new page to the notebook. Now, in a centralized ledger, we should trust Alice, and Alice has authority to stop servicing. And we want to avoid needing to trust a third party. So here we're going to do it by decentralization. But what is decentralization? Decentralization is simply replacing Alice with a multi-agent system. Instead that Alice be the owner of the ledger, a multi-agent system would be the owner of this ledger. And this multi-agent system could be a dynamic set of agents. Some agents could leave being the owner, or some agents could ask to be the owner of the ledger. So the owner should maintain the same ledger, although we have a multi-agent system. But it is not true to say that each agent has its own ledger. They are going to maintain the same ledger. And it is a really important way to do it in a way that they have consensus on the same ledger. And they also should provide services for users. If they do not have incentives, for example, to propagate the data of a user through the network, then users leave the using this ledger. So what is happening here? A user sends its request to some agent, for example, say Bob. Bob should propagate the user's data among the network based on a selection mechanism. One of the agents is chosen to be the next block producer, the one who is going to to produce the next page, write the data on the next page, and punch it to the ledger. Then the block producer publishes its page and broadcasts it through the network. It is necessary that all the nodes know the new page and to have consensus what is the ledger right now. But before that, all other agents, or some of them, it just depends on the consensus mechanism, check the consistency of the new page with the previous data of the ledger. And if they found it consistent, then they are going to accept it as the new page, and they would have consensus on the ledger. In proof of work, the selection mechanism, as I said, it is a selection mechanism that based on an agent is chosen to be the next block producer. Actually, in proof of work, selection mechanism is ex ante. All the agents compete with each other to be the next block producer. Each agent gather the data and try to solve a hash puzzle. Everyone who solves the hash puzzle sooner, he would be the next block producer. But in proof of stake, the selection mechanism is not a game, and people randomly proportional to the amount of their stake, they are going to stake the primary token of the blockchain. A set of agents is chosen for an epoch. There are some epochs, and each epoch consists of some slots. Then this set is called validators. One of the validators is chosen to be the next block producer, and the other validators check that the consistency of the block produced with one of them. And using their digital signature, they are going to punch this new page to the blockchain, to the ledger, instead of solving a hash puzzle that is done in proof of work. So I'm going.
So Rasoul, so this is this is kind of very again helpful. I'm sure for people in the blockchain field, this is fairly like well-known stuff, but like for somebody who's sort of trying to understand the nuances, so like is in the proof of work mechanism as well, there is an element of randomness, right? Like, yes, it is strategic, like everybody is sort of competing to increase their chances of being able to solve the puzzle by having more computational power. But there is an element of randomness. You can increase in expectation your chances of being the next creator of the block. And in proof of stake, there is still randomness, but it is in proportion to some commitment stake that you take on. So, like in both, it appears to me that there is sort of a commitment ex ante you need to take on, like either more computational power or more stake, and then that increases in expectation your chances of creating the next block. So, if looking at it that way, they seem more similar than dissimilar. So, like, what's my? Yeah, could you help sort of like? Am I looking at that wrong? Like, because in both cases, it seems like whether in work or in stake, you have to commit to sort of some additional resources ex ante to increase your chances of sort of being the block creator. So they seem similar in that sense. So what am I missing in terms of the difference between the two?
Yeah, actually, there are some differences. Here, computational power comes from the real world, from the outside of the blockchain system.
Right.
So some news get and say, okay, I want to be also a miner. And but in a proof of stake, it's all in its own system. So the chance is not coming from the outside. If I want to increase my chance, and I am a rich man in proof of work, and I do not have any Bitcoin, there is no problem. I'm going to add lots of new devices and increase my computational power and start to mine. But if I want to be chosen in, increase my chance to be chosen as a block producer in a proof of stake, and although I am rich, but if I do not have any stake, any primary token of that blockchain, I do not have any chance. So And surely proof of stake is not going to consume lots of energy, and it is that. Yeah. Do you have any other thing in your mind?
No. I think that's helpful, sort of coming from outside versus.
Yeah.
But I'm also curious in terms of, like, because you had started talking about sort of the incentives and the mechanism. So from a mechanism design perspective, it creates sort of, the incentives are different in the two. So, like, is there much research on sort of a mechanism design view of proof of stake versus proof of work?
No. Lots of work are done on proof of work, but so I can say that so many works are done on proof of stake. Yeah, we cannot say that both of them are studied equally, and but I'm going to in my next section of my talk, I'm going to talk about a set of axioms that can cover both of these mechanisms and both of these consensus mechanisms. Yeah. As I said, that we're going to replace Alice as the owner of the ledger with a multi-agent system. So my question here, what are the axioms of this multi-agent system that works properly and correctly? So I'm going to propose a set of incentive compatible axioms for decentralization, maintenance of a ledger. Why do we need an axiomatization? The axiomatization let us know and be aware of how to design an efficient decentralized ledger. If we have a set of axioms, for example, 10 axioms, 12 axioms, and we know that we should have concern about them, then when we are going to design, for example, a mechanism for a specific blockchain, we know how to design it. Also, I aim to drive blockchain security properties from this axiomatization and prove that, okay, it is secure and this attack does not happen to this blockchain because of these axioms. My axioms are categorized in two parts. One part are incentivizing axioms, and the other part are disincentivizing axioms. Incentivizing axioms are the fuel of the mechanism. Incentivize agent to maintain the ledger and run the ledger. And disincentivizing axioms actually disincentivize agents to not behave malicious. Axiom 1 actually says that every node should have incentive to become the producer of the next page or block. In both proof of work and proof of stake, we have two incentives for a miner, the one who is going to produce the next block. One of them is block reward, and the other is a transaction fee. And if we do not have any reward here, then why agents in the multi-agent system should cooperate, should contribute their computational power or their stake to produce the next block. Axiom 2 is about the incentives of propagation. As I said that we have a network and a user sends its request to the one of the agents or some agents in the multi-agent system. These agents should have incentives to propagate the data of the user between other agents, and all the agents are aware of it, and the agent that is going to next the block to produce the next block consider this data and put it in the block. So propagation also is important here. Neither proof of work nor proof of stake considers any reward for data propagation. Maybe we can do something. For example, we say, okay, if I receive the data from this node, I'm going to consider some reward for the node that who propagates this and in this data. And when I'm going to put the data in the block, the reward of the block also consider those agents who are going to sign the data and send it the data, and in the way who are going to propagate the data to make a block would have some rewards in the blockchain. Axiom 3 incentivize agents to make more contribution. Actually, the chance that a node being selected to be the next block producer is proportional to its contribution. I mean that if you want to design a consensus mechanism, it could be proof of work, proof of stake, or anything else. Axiom 3 is necessary. For example, in proof of work, the more computational buffer, the more chance to become the next block producer. And in proof of stake, the more staking, the more chance to become the next block producer. It is not. We should actually reward those nodes who are going to contribute more in constructing the ledger. Axiom 4 says that all agents maintain the same ledger and actually have consensus and agreement on the ledger that's going to construct it with each other. So all the agents eventually reach a consensus on the same ledger. And the longest chain rule in proof of work and proof of stake is guarantees that eventually reach to a consensus. What the longest chain rule says, the block reward for the miner, for the block producer, has value and is valid if this block is on the longest chain. So if I mine the block and it is not on the longest chain, then I would not have this reward. So in this way, the longest chain rule is, cause that we have a consensus on just one ledger, on the same ledger, and eventually leads to this consensus. Axiom 5 actually is to prevent a Sybil attack. If I want to be a member of the multi-agent system and act as an owner of the ledger, as I said that instead of Alice, we're going to consider a multi-agent system as the owner of the ledger. If I want to be one of these owners, it must have a cost for me. Okay, to submit to be the member of this multi-agent system, it should have a cost. If it does not have a cost, then people can run fake nodes without any cost, and it would be Sybil attack. In proof of work, the cost of membership is buying mining devices and contributing their computational powers. In proof of work, the cost of membership is staking primary token and the yield of the deposit stakes. I could go and consider my money in the bank and have the yield of that money, but I'm going to use this yield here. So it is the cost of being a member of the multi-agent system. Axiom 6 actually is a disincentivization to avoid malicious behavior. Actually, it prevents selfish mining attack. The block producer must get disincentivized to publish its produced block by delay. I'm going to explain what is selfish mining attack when the block producer in proof of work has incentive to not publish the produced block as soon as possible. Axiom 7 says that the block producer should not have incentive to fork the blockchain. If I have incentive to fork the blockchain, then we wouldn't have a ledger. We would have a tree, not a sequence. So actually, in both proof of work and proof of stake, there are incentives to fork and make another longest chain, but it depends on the on my computational power, on my power in this multi-agent system. So if I am an agent who has lots of power, then I would have to make a fork. I would have incentive to make a fork. Axiom 8 actually is about that I'm a block producer. Why shall I get services to the users of the ledger? If I can make a page and get the block reward, get the reward of the network, then I'm not going to consider the data and putting transactions in the block and write them on the block. So we have here transaction fees versus block reward. If the block reward is so high, then and transaction fees is almost nothing, then people can consider that putting no data on the block and publish an empty block, create an empty block and publish an empty block. Axiom 9 says no censorship. Actually, the block producer must be disincentivized to censor some users. And here is anonymity important. If we design a mechanism and a user can can authenticate the other users. An agent can authenticate users, then you may have incentive to censor them and not write their data or propagate their data. So, but if we use a public key and we have anonymity, actually Axiom 9 would happen. Axiom 10 says avoiding centralization. As I said, we replaced Alice with a multi-agent system with a set of agents. What happens if all of these agents make a cartel, or make a coalition? Then again, we do not have a decentralized ledger. So nodes should not have incentive to form a coalition and make the blockchain centralized. In both proof of stake and proof of work, every agent can act as a pool manager and create a pool and say, okay, I'm the pool manager. People, other agents can get to that pool and be the member of that pool, and that agent is going to, the pool manager propose a sharing strategy, and other agents decide based on the share strategy to join to which pool. Now, suppose we have some mining and staking pools, and let's talk about the sharing strategy. I say that a sharing strategy S1 dominates a share strategy in S2 if every agent prefers joining pool with a strategy S1 to joining pool with a strategy S2. So here it is the definition of domination, and a strategy S is dominant if it is not dominated, if dominates all other strategy, if it dominates all other strategy. Also, we say a sharing strategy is power compatible if every agent prefer a more powerful pool with a strategy S to another pool with the same strategy but with less power. So if we have two pools with the same sharing strategy, and this pool has more computational power, and I am a miner, I would like to join to this pool with more computational power. Now, if there is a strategy that's a sharing strategy that is dominant and it is also power compatible, then we would have centralization. Then we would have centralization. All the agents would consist a cartel. So if we want Axiom 10, then there should not exist a dominant power compatible strategy. So I propose.
Just a quick comment. So there is a paper, a 2020 American Economic Review by Jacob Leschno and Philip Strack, I think, on an axiomatic approach to blockchain, and they have 3 axioms. Have you seen that paper?
Approximate. Could you please?
So yeah, so it's a 2020.
2020.
Yeah, it's called
Yeah.
an axiomatic approach, Bitcoin and axiomatic approach. And they basically have three axioms which are contained in your axioms. One is um, anonymity, one is
Mhm.
robustness to Sybil attacks, and one is not no merger, the no merger axiom. And with these three axioms, they show that any protocol that satisfies these three axioms will have the same payoffs to miners as Bitcoin, right? So I'm not sure if you so yeah, I think the axiomatic approach is very helpful, but I'm not sure if you're familiar with that 2020 paper by Leshno and
No,
Strad.
no, unfortunately, I did not
Yeah,
see that paper.
I'll
Yeah,
email it to you. But yeah,
thank
no,
you.
I think they have just those three axioms which are contained in your 10. So yeah, but I'm sure you'll be interested. But yeah, please
Thank
carry on.
you. Yeah, it is interesting. Thank you. Yeah, actually, I decided to propose incentive axioms from this part. Yeah, but I'm going to read it. I would be thankful for sending me the paper. Yeah, here, in mechanism, one of the things is that possibility and impossibility theorems. So the first question that is that it is these 10 axioms, these 10 incentivizing axioms are possible together, and I need to answer. If it is, I should, no proof of stake and neither proof of stake nor proof of work are the model of these axioms. Some of the axioms are not satisfied in proof of work, and some are not satisfied in proof of stake. So we should think of it. Can we find a model for these 10 axioms? The other thing is game-theoretic security. And what's the difference between game-theoretic security and cryptographic security? In cryptographic security, the security obtained by cryptographic primitives, hash functions, asymmetric cryptography, symmetric cryptography, one-way functions, and so on. But in game-theoretic security, actually, we may have a protocol that is not secure in the concept of cryptographic security, but it is secure in the game-theoretic security, as the attackers has no incentive to attack, or disincentivize actually to attack. So it's another notion of security here. The second question is that are all these axioms are enough and complete to prevent game-theoretic malicious behavior, and no agents wants to attack and act malicious. I'm going to here refer and talk about some famous and well-known threats. Selfish mining attack, 51% attack, and long-range attack in proof of stake. A selfish miner actually is a miner who produces a block, keep it private, and is not going to publish it. So I'm a selfish miner. I produce the block. You may see these red blocks. I'm going to produce the block, and I should publish the block to get the rewards. But I'm not going to publish it. I'm to keep it private, and I start to make the next block on this block. So why? My reason is that I want to get the rewards of more than one block. So it is my incentive. And if an honest agent create a block sooner than me, as I did not publish my block and keep it private, I would lose the reward of that block. So, but if I have the chance, if I am enough powerful and to be enough fast to make a longest chain with 2 or 3 blocks, then I have incentive to attack as a selfish miner.
So Rasoul, I just wanted to give you a quick heads up about the time. So we probably have only a few more minutes left before people have to leave for other. I can stick around for a few extra minutes, but just wanted to let you know.
Yeah. So I'm going to very quickly review these attacks. Thank you so much for your information, for giving me that. Yeah, here the risk is that the selfish miner wastes his computational power. There are two incentives for here: incentives for being selfish, gathering rewards of several blocks, and incentives for being honest. In that, if I do not publish my block and someone else publishes block, then I would lose. So to satisfy axiom 6, it is needed that the expected benefit of being selfish is less than the value of wasted energy here. Another attack is 51% attack. Actually, if someone or a cartel can make the longest chain, then actually he could make the double spend. But if we are sure that there is no agents or cartel that can produce the longest chain independently, then it is proved that the strategy profile of not forking and continuing the longest chain is a Nash equilibrium. It is proved that actually following the longest chain for all the block producer is the Nash equilibrium. This is strategy profile. But if there is an agent who controls more than 50% of the network computational power, and he can build a fork faster than other nodes, then that attacker actually can make a chain faster than others and double spend their tokens in the original chain, and after that publish its chain. And as people all are going to follow the longest chain, and the longest chain rule says that the ledger is the longest chain rule, it could do double spending. But why double spending does not happen? Even if an attacker has 50% of the network computational power, there is a disincentivization here for him to not attack. Suppose that if a 51% attack happens, users lose their trust to the blockchain and leave the blockchain. As soon as they lose their trust, the primary token of the blockchain, for example, Bitcoin, lose its value. And as soon as the value of the primary token lose its value, the blockchain, the one who has the 50% computational power, also has lose the value of his block rewards that he has in the blockchain. So it disincentivizes him to make the attack. So although I'm going to double spend, but as soon as I double spend, then nobody's going to trust the Bitcoin. Nobody's going to trust the blockchain. So I'm not going to attack. And none of the 10 axioms that I discussed is going to prevent 51% attack. Actually, in tokenized blockchain, we could have another axiom. We should think of another axioms that considers the value of the token. But in all of the axioms that I talked, we do not going to talk about the value of the primary token. But what if the blockchain is tokenless, and how to prevent 51% attack in tokenless blockchain when the wage of the block producer comes from the real world outside the blockchain? We have a long-range attack in proof of stake when the validators who validate a block in a long time ago and do not need their private key, they're going to sell their private keys to an attacker. An attacker, starting from long time ago, can make an alternative chain. So some blockchains use checkpoints here to avoid long-range attack. And as we see that, again, my axiom just can avoid selfish attack, not 51% attack, and not longest range attack. So finally, to build a decentralized ledger, cryptography is the punch. Mechanism design is the decentralization and in the Multigen system. Having an axiomatization for incentive compatibility of decentralized ledger help us to know what an efficient design could be. And having an axiomatization, we can verify game-theoretic security, which differs with cryptographic security. These are some references of this talk.
Great. Thank you so much, Rasoul.
So much.
I think this was, for me at least, very, very interesting. Do you have like a write-up for these results, not in presentation form, but in a paper form?
Not completely. It's not yet finished, but I'm working on it actually.
Okay.
Yeah.
Please, I mean, I'd be very happy to, receive a copy when you have it, because I think there's a lot to learn. We've talked about sort of opportunities for, collaboration, and I'm sure there'll be some ideas that can come out of that. So, and of course, I'll be in touch by email. But thank you very much for taking the time, and thanks for everybody else who's online. This was certainly a very helpful talk for me, because I've been thinking in terms of incentives in blockchain, maybe not in sort of like cryptocurrency setting, but more in supply chain setting. But I think many of the ideas apply. Maybe there are some different issues in that setting, but very interesting talk. So thank you so much.
Thank you, Harish. Thank you so much. Thank you, Chang. I'm also interested in collaboration. Let's be in touch with email. I'm interested in applications of blockchain and mechanism design in supply chain and other topics that you are interested. Let's see what we can do. And I'm eager to learn more from you and others. Yeah. Thank you so much.
And very happy to set up this connection. So hopefully we'll of course be in touch more. And thanks Chang for setting it up, and thanks everyone else for attending. And see you later, Rasoul. Thank you very much.
Thank you. Good morning and good night to everybody. Bye.
Thank you, Chang. Bye. And thanks, Rasoul.
Thanks, Chang. Thank you.